I'm Eric Drexler, and I was drawn into the field of what's now called nanotechnology when I was a student at MIT back in the 1970s. And the center of my work has been understanding what physics tells us about technologies that don't exist today, but that could be developed in the future.
Can you just speak a little bit about the history of nanotechnology, from the first stirrings of the idea to your own work and what we've done since then?
What I tend to think of it as is the steady progress that people have made in control of the structure of matter at a very fine scale, and in particular with atomic precision. It was more than 100 years ago that chemists started designing and deliberately building atomically precise nanostructures in the form of synthetic molecules. Progress in understanding that grew with quantum mechanics. It grew with the growth in techniques in chemistry. The understanding of what can be done grew with the understanding of molecular biology, molecular machinery in cells. In 1959, Feynman famously pointed out that one ought to be able to build machinery that can maneuver things with enough precision to build molecules in a controlled way. Then later I published my 1981 paper in the Proceedings of the National Academy of Sciences that said, hey, given the technologies that we see emerging, it seems there's a path open to building the sorts of things, developing the kinds of capabilities that Feynman pointed to, and outlining a range of applications that went beyond what had been discussed before. Subsequent to that, I had a series of publications. People became more and more interested. The label nanotechnology became very popular. People promptly found that it could be applied to areas of chemistry, molecular biology, material science, fine-scale lithography of the sort that we now see in your computer. Desktop computers can now be called nanotechnology quite legitimately by present definitions.
What was the main idea in your engines of creation 20 years ago, and how far have we come in proving the feasibility of these ideas and implementing them?
That there's a pathway open from our present technology, step by step through more advanced fabrication technologies, that starts with atomically precise things we can build today and moves toward a very broad ability to manipulate matter at the molecular scale, building atomically precise systems with high performance. Since 1981, we've seen enormous progress, both in understanding what can be achieved and in laying foundations, moving forward toward these objectives. Since then, at the theoretical level, the use of computational modeling techniques to understand what physics tells us can be built by carefully arranged molecular structures has shown that we can build computational systems that are far denser than we have today, materials that are far stronger, and so on. At the experimental level, we've seen progress from being able to make only relatively small and simple molecular structures to being able to design and fabricate structures on a scale of thousands to millions of atoms in a precise organization. And this is building on molecular machinery and biology. The expectation looking forward is that we'll be able to use that ability to make molecular machines, like those found inside the cell, that take simple molecular building blocks, put them together, and make building blocks that can then be put together to make larger systems.
Let's talk a little bit about what the potential of this would be. One thing we can build is very powerful computers. So could you give us some idea of the comparison of the computers we could build ultimately using nanotechnology to what we have today?
In the area of computation, there's a very conservative design for computational systems that can be the basis for building computers that are comparable in power to modern CPUs, but occupy approximately 1 cubic micron. And putting the power of a modern-day computer, modern-day CPU, into a cubic micron lets you deliver that kind of computational power in a volume that's about 1/1000th that of one of the cells in your body. And I think that says something about the kinds of tools that will be available for biomedical instrumentation and intervention in the future.
Now, another promise of this technology is to have basically tabletop factories, but factories that are not big buildings, but that sit on a table that can make what?
Macroscopic kilogram scale objects in which the components and materials are as good or better than the best that you find in experimental laboratories today. That means, for example, materials that are 50 times stronger than what the space shuttle is built out of. Computers where, again, a CPU can fit into a cubic micron. And looking at the costs of these products, you could look at the energy required, you can look at the materials required, you can look at the cost of capital, labor, etc. The costs seem to come out somewhere in the dollars per kilogram range, which is rather inexpensive considering that the capabilities will be beyond today's state of the art.
So basically, physical products become information. I mean, right now you can take an information file and create a movie or a music recording or a book. So we'll be able to take information files that describe some physical object and create most of the things we need in our daily lives.
Yes, the way to think of this is very much as a nanoscale components being the starting point for manufacturing of the sort that we see in macroscopic factories. And increasingly, those factories are automated systems that are using processes that were designed in an automated way by software to make products that were designed in software. One concept for how a nanofactory could be organized to have high productivity, despite the fact that the materials being handled are at the scale of individual molecules, would be to have a two-dimensional array of micron scale, actually somewhat smaller devices that are processing small molecular fragments. They would put these parts together to make larger structures. The next layer would put those together to make larger structures, and so on. So you would have many trillions in the first layer, progressively fewer, progressively larger products, until out the other end you would have things at the macroscopic scale. And if you just do the physics-based analysis of that, you find that the production rates can be very high, that a system that sits on your desktop could produce its own mass in sophisticated products in a matter of hours.
Neil Gershenfeld has a concept called Fab Lab and refers to your work actually as the goal, and he articulates his own vision of a roadmap, basically going from what he currently has is sort of multi-micrometer features, micron features, to finer and finer features, ultimately down to multi-nanometer features.
Well, broadly speaking, there have been two ways of approaching control of matter at the nanoscale. One is top-down, which generally hasn't given atomically precise control, but is moving down toward a scale that is similar. The other one is bottom-up. You start with atomic precision, and you build larger and larger, more and more intricate structures as you go along. The top-down approach, which I gather is what Neil is pursuing, I think is likely to sort of meet in the middle with the building up from the molecular scale.
How do you see these two worlds interacting? I mean, can we learn lessons from biology? Can we actually use components from biology? Can we take biological systems like cells or ribosomes and modify them to create other nanomachines? What's the interaction between the biological world and what we're trying to create?
The most central interaction, from my point of view, is the use of the molecular machinery found in cells, programmable, productive machinery, to make components. Your cells contain ribosomes, which are programmable machine tools. They take in RNA, which has information from DNA. That RNA tape, its digital information, is used to direct the construction of protein molecules, which are little chunks of material that are about as strong and stiff as something like polycarbonate plastic or epoxy. And they're the building blocks for molecular machinery in the cells. So you have a molecular machine that can be controlled to make components for more molecular machines. What we're learning to do is to program this biological machinery to make components that fit together to make structures designed by scientists and engineers. At present, one of the most impressive technologies is called structural DNA nanotechnology, which uses DNA not as an information molecule, not as a genetic molecule, but as a structure. You have the double helix and you treat it as a cylindrical strut. They can be linked together by having strands cross over from one to another. And researchers have made structures on a scale of millions of atoms. I think, though, that we'll very rapidly find that the non-biological materials are, for engineering purposes, better. And at that point, biology will be more teaching us lessons and being an area of application. Early products I would expect to include a wide range of instruments that are useful for biomedical applications, for example.
You've talked about the interplay between nanotechnology and artificial intelligence, and which might come first and how one might help the other. Can you comment on the interplay between these two revolutions?
It's certainly possible to develop nanotechnology, advanced nanotechnologies, without AI. On the other hand, if you have advanced nanotechnologies, they will give enormously more computational power, which should be an aid to developing AI. And if you had advanced AI, it would be something that could be a great aid to design and therefore would facilitate progress in nanotechnology. So neither one is necessary to the other. Either one can help the other.
A few decades ago, there was a conference, the Asilomar Conference, that established some ethical guidelines to keep genetic technology, the idea of biologically modifying viruses, safe. And they've actually worked very well for 3 decades now. What role do you see ethical standards playing in nanotechnology, and what do you see as the key sort of safety issues to keep this very powerful technology safe?
Looking at terrorism, I think the first thing to observe is this is a very sophisticated technology that will be in the hands of governments, corporations, long before it's in the hands of people who are in smaller groups and are outside the sphere of open technology development and activity. At some point, though, powerful technologies, as we've seen, tend to diffuse, tend to become widely available, and there are often things that can be done with them that one very much wants to suppress. And I think that if we look at the future, where technologies are going, even without nanotechnology, just with Moore's law progress, we're seeing a greater and greater density of sensors and communication systems. I think that the concern that people should have downstream a decade or two isn't that there will be terrorists doing things that threaten them, but rather that systems that have been put in place to, among other things, suppress terrorism will have succeeded and may be used to suppress things that they would prefer not be suppressed. So people have been saying that terrorism will be a long, open-ended war. If you look at this from the perspective of technology, I think that even without nanotechnology, that we're moving toward a world of intensive networked surveillance systems that will be able to suppress whatever people want to suppress. Terrorism is very much a passing problem, and that our concerns should be focused on how to manage the technologies that will make terrorism no longer be a problem, how to deal with a world in which there is that degree of ability to observe what people are doing and to control human action. One answer to the question of why people should develop nanofactories is that at some point it will be so easy that it will be the obvious thing to do. People right now are developing increasingly sophisticated nanotechnologies because, well, there's interesting science in developing some of the components, and there are practical applications. Every step is a step in increasing the control of the structure of matter. That's been sort of the story of much of technology for a long time. So progress in this general direction is a natural, spontaneous unfolding of technological advance in a worldwide sense. Another facet is taking the Moore's Law progress further than can be done with semiconductor processing. Another facet is looking at the cost reductions that we expect to see from these technologies and the very small resource requirements and the ease of providing power using solar cells that can be made with the same technology. This will provide a basis for taking everyone in the world, people who are dirt poor today, and providing them with a standard of living that's far beyond what we have in the developed world today, and with less ecological impact. I think that the most important thing to understand about all of this is that the technologies that we're moving toward will be very different, very much more capable than the ones we have today. That will certainly raise some new problems, but it will also give the ability to solve what today are regarded as some very large and intractable problems, including things at the scale of climate change, changing our energy system in a fundamental and large-scale way. So when I look at the world, I see a set of urgent problems that is really quite different from the ones that dominate public debate today. The greatest difficulty that I see in developing advanced nanotechnologies is a difficulty that's more cultural, really, than scientific or technological. What we're looking at here is the emergence of a new field of engineering from an area that has been a set of areas, convergence of areas, that have been in the field of science. Scientists are used to working in small teams, exploring new frontiers. Engineers, to build large systems, work in larger teams, and they seek their challenges in taking known phenomena, known components, and building new systems of sorts that haven't been seen yet. So having a culture of systems engineering, developing that in the world of nanoscale technologies, I think is one of the greatest challenges we have today. Regarding the question of whether the singularity is near, I think it's, in one sense, very hard to say. But what I think is clear, and what I think is widely believed by people who are thinking about history and the development of technology with sufficient perspective, is that on a historical timescale, we are very close to an unprecedented and enormous and swift transformation of human life and the world.